This lecture is a laboratory session in the sense that we create a mathematical model, we put on boundary conditions, we put on loads, and then we observe the results. We're going to look at the normal modes of vibration of a cantilever beam. First of all, I'll give a problem statement. Then we'll go into the physical modeling. And separate from that, I'll discuss the finite element modeling. I separate these two out because years ago, in talking with Jerry Joseph at the McNeil-Schwindler Corporation, he claimed that fully half of his questions in customer service had to do with physical modeling and really nothing to do with finite elements at all. So the physical questions, whether it's a beam or a plate or a solid, what the boundary conditions are, can be separated out, and then those questions that are actually finite element related can be separately studied. We're going to study 3 different solutions using MSc Nastran. We'll use the modified Givens, the inverse power, and the LAN Choice methods. Then we'll look at the results that we get from those 3 methods and compare those with classical theory. The problem we're studying is a straight, uniform cantilever beam. It is clamped at the wall, shown here. The coordinate system is such that the vibration is going to take place in the XZ plane. So I'm interested in how this vibrates up and down on this page. The tip is free. The beam is 3 meters long, and I've chosen its characteristics to resemble that of a fighter aircraft wing. It's also about the same size as a diving board for a swimming pool, so maybe some of you have such a pool near where you live, and we're going to get natural frequencies where the lowest frequency is about 10 hertz. This is made of steel with a Poisson ratio of 3/10. We use density shown here, and we're in the Newton second millimeter system. That means mass units are in megapascals. Here's a picture of the cross-section with the 100 millimeter high and 150 millimeter wide section. It means the beam will have its lowest modes in the XZ plane because it's weaker in that direction. The question of whether this is a slender beam or not is resolved by looking at the height to length ratio, 1/30th, and that's certainly adequate to be in the range considered slender because it's greater than a ratio of 10. I've calculated the moments of inertia for the cross-section, and they're shown here. Our goal is to find the first 2 natural frequencies for the flexural vibration in the XZ plane, ignoring the axial and torsional motion and the out-of-plane flexural motion. In other words, the motion in the XY plane. So our coordinate system is shown up here again at the clamped end. Later, when we want to look at figures of the normal modes, we will tend to look at this in the XZ directions and into the Y-axis. So we'll be looking from this direction to see the vibration modes. Now the physical modeling, we're going to use simple Euler-Bernoulli theory. This is found in the bar element in Nastran. Under that theory, you're allowed to uncouple the motion in the axial and torsional directions as well as flexure in the Y direction. And that's due to the linearity of the problem, and we have symmetry of the cross-section so that those are principal coordinates in terms of the geometry of the problem. So basically, we're only looking at the lateral deflection W of the centroid of that cross-section as a function of x and time. Now let's proceed to the finite element modeling. For academic purposes, I'm only going to use 2 elements. That's so that the viewer only has to do a minimum amount of typing. Originally, when I did these problems, I had to choose simple models for another reason, and that was computer cost, because I was paying hard dollars in my large classes. I was the second largest user at the University of Michigan College of Engineering when I started doing this training some 20 years ago, so I had to really watch the usage on computers. Now with workstations, a person can occupy that workstation as long as you have the endurance to do, and as long as the computer endures. We're going to use a simple beam element and the bar element in Nastran, and we're only going to use two of those, shown here and here. I'm showing 3 nodes. At the outset, using the conventional computer program terminology with degrees of freedom 1, 2, 3, 4, 5, 6 at each node, we're going to constrain degrees of freedom 1, 2, 3, 4, 5, 6 at the wall, knocking out these degrees of freedom shown here. Then by constraining the remaining nodes in the axial, out-of-plane flexure, and torsional motion, we are going to knock out all but these remaining 4 degrees of freedom here in this rectangular box. So the reduced problem after boundary conditions and constraints are applied only has 4 degrees of freedom. Now, because this problem has 4 degrees of freedom after it's been reduced, you would expect to only have 4 natural frequencies of vibration and then 4 associated modes. Now, it's fairly easy to solve this problem, so it's not a matter of laboring for a long time over which method to use. We'll in fact use 3 different methods. But there are ranges of degrees of freedom and number of frequencies desired which would restrict your choice of methods. There's an older chart shown here, and times change, so this is like a moving target. But one can look at the number of degrees of freedom here, and of course we're way down at the bottom end, at the trivial end, at 4. But for smaller systems, you can use the modified Givens method. This method finds all of the frequencies for the whole system, and then as many eigenvectors as you wish within a given frequency range. So we'll demonstrate that. The older inverse power method is shown here as a method that you might use when there are possibly a larger number of degrees of freedom and therefore a larger number of candidate modes, but you only want to find perhaps a few of them. That's a pretty good method for that. That's this little inset here. And then for more moderate degrees of freedom when you want larger numbers of modes and frequencies. LAN Choice is tending to win today. It's starting to displace the other methods. I think you would find many people that would use LAN Choice on out to the right here. So I think unless you are a fan of component mode synthesis, probably today LAN Choice is starting to win. The Givens and modified Givens method can still be used in a more of a restricted range. You probably ought to speak with people at your own company on what your experience has been with your product. Sometimes you have larger bandwidth, sometimes smaller bandwidths, and that also can have something to say here about which method to choose. Our first numerical solution for the vibrating cantilever beam will be done with the modified Givens method. This is a matrix transformation method as opposed to an iteration method perhaps. It's related through the eigenvector solver to the inverse power method because they both use the inverse iteration for the eigenvectors. We're going to get all of the eigenvalues for the whole problem, for the whole frequency range, and then we're going to specify a range of frequency where we get the eigenvectors. So that's a little bit unexpected to see that distinction between the eigenvalue solution and the eigenvector solution. We're going to use Sol 103. We'll arbitrarily call the eigensolution method 97. That's just a flag that points down to the bulk data. And here's the EIGR, the real eigenvalue solver with this arbitrary number 97. We're asking for modified givens. Our frequency range is going from 0 hertz to 2000 hertz, and that's the range over which we will get the eigenvectors found. We'll get all of the eigenvalues, but only these eigenvectors lying in this frequency range. And we'll normalize those eigenvectors by their maximum component. Let's look at the data set for our modified given solution. Here's the file management statement. Then our executive control statements include the identification here. These can be 2 8-character words separated by a comma. You should start with an alphabetical letter here at the start of each. Time is given in minutes. We're using SOL 103, and that's the end of our executive control. Case control has a title. We were using a subtitle. That's more often used when there are subcases, but we don't have but one case of loading here. Well, in this case, it's just one eigenvalue solution. And then we're going to echo back the sorted data. Let's continue with the case control commands. We do want the displacements in this problem. I'm not interested in stresses. Here's our eigensolver. I'm going to ask for element strain energies. We're going to use Nastran plotting here, from here on down. We're going to include all of the elements in the problem. We're going to look into the minus y direction at the origin, and then with x to the right and z upward. So that's the side view of the vibrating beam. And our view angle won't be rotated. Then we'll locate the figure properly on the page. And we'll plot our modal deformations, including the undeformed position. And we'll plot all 4 modes. Bulk data is shown next. Here we point out the grids. We have only these 3 grid points. They're given in the basic coordinate system here, which defaults to 0 in this column. Then we give the x coordinates here in the first entries. When you get toward the end here, you have the coordinate system that output is presented in, and some of the calculations are done in, and constraints and so on. And then here are the constraints for the first grid point at the wall. All 6 displacements are constrained. For the other nodes that are outboard, we constrain the 4 degrees of freedom here, preventing axial, torsional, and out-of-plane flexural vibration. We now continue with our bulk data, and the next entries are the connectivities. We have 2 C-bar cards for elements 1 and 2. Those both have the same property card, 37, which is pointing below to this entry. Element 1 joins nodes 1 and 2. Element 2 joins nodes 2 and 3. Then the vector shown here, the vector v, is the vector that lies in the 1 plane. In fact, it defines the 1 plane. Earlier I had said this was going to be the xy plane. In fact, you could have picked an arbitrary direction for the 1 plane. When other things are equal, I'd recommend that you do have it lie in xy plane just to keep your notation common from problem to problem. And then I use that same directional vector for the second element. The property card here, property card 37, has a material card 25, which it points to, and that gives you then the triad of a connectivity, a property, and a material card. The property card points out the area here, cross-sectional area in millimeters squared, and then I1, which is the moment of inertia that opposes flexure in the one plane, and that would correspond really to the IZZ. And then this one here is I2, which is the moment of inertia tending to prevent motion in the two plane, and in our problem that corresponds to IYY. And this is the one that is of interest to us. That's the lesser of the two moments of inertia. Our materials are those here of steel with modulus of elasticity. We leave out the shear modulus, we put in Poisson's ratio, and we put in density here in megagrams per cubic millimeter. We've already explained the Eigensolver card, EIGR, with the modified givens called out, the frequency range over which we want our eigenvectors, and then the normalization of those vectors by their maximum component. There are other normalization methods, of course, available too. We will ask for coupled mass in the mass matrix, and that's this parameter. We set that to be unity to turn that on, and here's our post-processing here, post -2. This run was launched from a workstation and was then sent to a larger Hewlett-Packard machine for execution. Nowadays the codes are getting so strong, the computers are getting so strong that often the average engineer has a workstation with a finite element code directly loaded on their machine or directly accessible, if you can afford that. Some systems like mine at the University of Michigan have centralized copies that can be executed at a certain restricted number of stations simultaneously, perhaps 50, let's say. I've printed out some of the output from this run so we can look at the details. Here's the sorted bulk data echo to show what the data were that we read in, and that's always nice. This is the form of the data deck that is most easily read by other people. Each individual puts cards in their own order according to their own feeling, but this sorted bulk data echo comes out identically no matter who wrote it, because it resorts and does things in a logical order. So for instance, when I grade students' work, I would prefer to see this sorted data to check for errors. Then the results obtained by the modified givens method are shown here. The eigenvalues in cycles per second are illustrated here in this red column. The first natural frequency is approximately 9.2 hertz. Then we have 58, 197, and 572. Now there would be other modes of vibration that would lie intermediate to these. Only the lowest one is the lowest flexural frequency. I'm pretty sure the sideways bending of the beam would be a frequency somewhere either in between the first and second or second third here. Likewise, I'm not certain where torsional would be. Torsional might well be even lower than these. It's just hard to say. I doubt it though. And axial certainly would be high. So what about all I can say here is, unless we solve for all of those frequencies, that we're just getting a subset of all possible frequencies, and certainly going for the lowest one here, the lowest flexural frequency, and would have to check the torsional frequency to see if that would be lower than this. Be a little careful in using MSC Nastran for torsional vibration, because sometimes the rotational inertia for the cross-section is not included automatically. Another one of my professors has commented on that, and so I would ask someone carefully before you do torsional vibrations of bars and make sure you understand the torsional inertia and whether you have to put that in separately. Here you can see in this set of numbers that the maximum displacement at the third node in the translational direction is unity. My header here has wrapped around in the way that I have printed this. This R3 should be back up here, so you can ignore that. And these are the Z translations at the different frequencies corresponding to these frequencies up here. So this is a little bit tricky. This is mode 1 that has the maximum translation of unity, which would undoubtedly be at the tip. Mode 2 has a maximum displacement of unity and probably at the tip. When you get to the third and fourth modes, it's not quite as clear because these could occur in an interior location. I think on this problem they typically come out when we look at our figures all at the tip though. Nevertheless, that's where the computer graphics helps you because you look at the modes and then you size them up one by one. I'll now show you some of the eigenvector data just for completeness. Here is the first eigenvector. And here you do see that the maximum deflection's at the tip, likewise on the second, yes on the third, and yes on the fourth. This would allow you to do a hand plot if necessary and to use the rotational information. Now the plot packages generally don't use this rotational information, and as a result they're not able to plot these eigenvectors from here on down. Why? Because they don't use but two pieces of information, and you can't distinguish among four modes with only two nodes being plotted. You'll see that in a minute when I show the modes. Let's change methods now and use the inverse power method. We ought to be comfortable with this method because we looked at the theory rather carefully, and you should understand that by now. In this case, we're going to look at the frequency range from 0 to 2,000 hertz. From our previous solution, we know that will gather in all four natural frequencies. Now, here below, I'm quoting the exact frequencies, which are known from classical theory. And so, indeed, we are going to capture all of those frequencies. So, we've got inside information, and of course, that helps us. Typically, you're asked to guess how many there are in that range, and you'd like to guess enough that you don't stop prematurely. And then on top of that, there's a second indicator, ND, that will be a number desired, at which point you will stop finding frequencies in that region. The default is 3 times the number of estimated frequencies. And so, for instance, when we put 4 in for the estimated frequencies in the range, the MSC Nastran program will stop iterating when it finds 12, or in other words, 3 times the estimated number. If you leave that blank, and as the MSC Nastran program continues to mature and improve, probably there will be tighter default numbers chosen year in and year out. So sometimes it's better to let the machine do that choice. I'll show you some of the output from the inverse power run here. And the one thing to notice is that I'm going to use the Sturm sequence inverse power. It's a modification. And from what I can see, that does have one effect. Not only does it give you more indicators of whether you're successful in finding all the frequencies in a range, but it also changes the order in which you find the frequencies. So for instance, if I jump down below, you'll see that it actually finds the higher frequencies first. And that's opposite. If I don't use Sturm inverse power, if I just use inverse power, then it will find them in the order in which we expected to from the basic theory. It would find them in this order. I've rerun that and checked that. But this is a better method today because it gives you more insight into what is happening. We have pretty much the same information here. This time, though, differing from the modified givens, we not only give a frequency range, but we're forced to guess how many frequencies lie in that range. The other data are pretty much the same. And it turns out the answers are very much the same. So our convergence is excellent. Let's look at the spectrum of frequencies in which we're interested. Here we see we range from 0 to 2000 hertz, which was our range of interest for searching for eigenvalues. We expected 4, and the number of estimated eigenvalues was set at 4. We know that in this case there actually are only 4, so we got them all. Here's some diagnostics printed out. There was only one starting point used. 5 decompositions, 49 iterations. For the Sturm inverse power method, we found those in the order of the smallest one first on up to the largest eigenvalue. Interestingly, if you rerun this just on the normal inverse power method, you then get the convergence in the opposite order from the top one down. And this has to do with your number of estimated eigenvalues causing a shift point somewhere in the middle of this region, and then the inverse power method converging to the nearest eigenvalues first, as shown by these in this order. So you can adjust the order of convergence by which method you use and by the number of estimated eigenvalues. A final comment at the bottom here is unrelated in a sense. It's just that node resequencing is automatically done in Sol 103, so the user doesn't have to ask for that explicitly. When you use the Sturm inverse power method, you get some additional diagnostics, and you are told how many eigenvalues there are beneath certain test frequencies. And this really is valuable. Historically, people had trouble when they missed modes, and that can be extremely bad for instance, an aircraft problem where you may have some potentially dangerous vibration situation in air. But this tells you how many there are below each frequency, and this will tell you, yes, indeed, there are only 4 frequencies and modes below 1400 hertz. Now that's extremely useful information, it turns out, when you have large systems. And again, I've shown here where the test points are as these little X's, and then the O's are where the true frequencies are. And so it's pretty easy to see why this, at this test point, it said all 4 of these frequencies lay below it. At this test point, or trial eigenvalue, it says there are 3 lying below that, and then so on. At this test point, there are 2, 1, and 0. So I think for the beginner, this may not look important, but I know for some old-timers, they would have loved to have had this 20 years ago, because, or whenever it was brought in. I think, my memory, it might have been 12, 15 years ago that this was brought in. And so this can be a lifesaver. Our third and final solution method is LAN Choice method. This is a modern, very popular, very productive eigensolver. Boeing company has done a lot of the programming in this area, has sort of led on the development of the method. It's also, of course, popular at many universities. When we do a LAN Choice solution, we make a couple changes. Here I'm changing the subtitle of the run to indicate we're using LAN Choice. That's trivial. Our method card aiming down at the solver now is called EIGRL for a real LAN Choice eigensolver. And we're going to take a frequency range arbitrarily between 0 and 1,000 and normalize on the maximum value of the eigenvector. And that's as opposed to perhaps a mass normalization. The extraction order here occurred from the lowest to the higher eigenvalues, and the numbers that we get are the same. LAN Choice has proven really good for really large systems, so you'll want to be familiar with this. The theory for this is harder than for the others. I'm still Now let's look at our results, and I'll show the graphical results and tabular results in the next two figures. Here are the plots of the eigenvectors, and because this is such a simple approach to the problem, I find that the eigenvectors that are plotted below the first two are not of any value. The reason is we only take the lateral deflection of that node and draw straight lines through it on the graphics package. This is a weakness of the graphics packages, and most of them are this way. They don't want to do a spline and use the slope information, and fit a parabola through there, say. So the first frequency is as you would expect, that the body will vibrate between a rather gentle curve up and a gentle curve down and move between those two extremes at 9.2 hertz. And the error in the frequency is very small. In the second mode, you expect to have a internal Chladni node somewhere along the beam, and it's about here. The first node has moved out of phase downward with the second, and so you get this, again, a kind of a nice shape. See how good an artist I am if I can illustrate this so that the beam moves back and forth between these two extreme positions, and that one is within a % error. Now the third and fourth eigenvector plots are meaningless because they lose the sense of the problem. This one actually has 2 zero crossings and indeed should be going down and up and down again, and the fourth one should have 3 zero crossings. Let's see, I think I may have done one too many there, but I think you get the idea. Let's see, 1, 2, 3. I guess I may be close there, but there isn't enough information to really accurately plot these. And also notice that the margin of error here has widened to be too crude an answer to be useful for most engineering purposes. I've often used the number of 5% as sort of engineering accuracy in problems. Actually, there are a number of cases where 10%, if it's really absolute error, would be adequate as well, but somewhere between 5 and 10% is considered useful. But when you get up into the above 20%, you're starting to get a little bit weak on your results. In our final figure, we'll compare our results with those from classical theory. Here are the analytical values from the Euler-Bernoulli beam theory, and these are taken to be exact within the physical modeling that we've done. We then see that the modified Gibbons method, the inverse power method, and the LAN Choice method give the same results within the approximations of a 2 finite element model. However, they do differ from the exact answers within the Euler-Bernoulli theory. So you can think of this then as a modeling error over in the right side that is due to the discretization in this problem. Presumably we could drive this to 0 in the lower modes by taking more and more elements in the problem, giving more and more degrees of freedom. We've sort of confirmed Rayleigh's original idea that you need twice as many degrees of freedom as you need accurate eigenvalues. We certainly get engineering accuracy in the first two and fail in the other two. I don't want to overdo this idea about having enough degrees of freedom, because the practical problem in industry is exactly the opposite. Most dynamic studies result from a model that has been constructed either for static stress reasons, nowadays called durability, or from just a need for a lot of geometry definition, holes, folds, design features that require a lot of degrees of freedom to describe. And so usually in industry, the problem of the dynamicist is to simplify a model that already has way too many degrees of freedom. And so if your all-up vehicle problem has a million degrees of freedom, you don't want to do a dynamic analysis with that many, and your problem really is to condense out degrees of freedom. Some people can do this in certain physical problems by mesh coarsening. That's another approach. Often that's done in acoustics. But I would say that the normal dynamics problem needs to have further work done on it to reduce the degrees of freedom, either by simplifying the model geometrically or by mesh coarsening, or by various nodal condensation and modal condensation methods.